In this video, we're going to work a Nernst equation question that's on the homework. It doesn't have an answer, so I thought it might be nice to work through it. This is just your plain vanilla kind of Nernst equation question. It's talking about two hypothetical metals, X and Y, so we don't have actual metals to look at on a table. And we have an equation that we're being given here. We have 3 lots of X, 2 lots of Y in the +3 oxidation state going to 3 lots of X in the +2 oxidation state, and 2 lots of Y. So to put it in the parlance, we can say that basically X has displaced Y from solution, would be a way in which we can put it. So one thing we can do real quick, just as some practice, is see if we can put a cell diagram to this, because this isn't a cell diagram, this is the reaction right now with the molarities in it. So if I make a cell diagram, here's my salt bridge. I'll put reduction on the right. So let's think about my reduction. What's changed its oxidation number? Well, these are both 0, and these are +2 and +3. So we can see what's gone up, what's gone down. X has gone from 0 to +2, and Y has gone from +3 to 0. So there we are, Y got reduced. So we can write Y3 plus aqueous, and we can put 0.330 molar. Then we have our line, and then we're going to have Y. We're going to make the assumption that Y would be a perfectly good enough material to connect to. Something, you know, it's fairly stiff, like copper or something like that. So there's my reduction side. And then my oxidation side, this might come out a little bit messy, but we'll give it a try. We're going to make the same assumption. We're going to say that X also can be clipped to. So we're going to have X solid. There's my line. And then we need our X2 plus. So X2 plus, aqueous, and we'll put 0.0440 molar. Just about squeaked it in. So there's a cell diagram that I've made from it, showing reduction on the right, oxidation on the left. Let's go ahead and calculate the actual reduction potentials, the actual non-standard cell protection we're going to get from this, because obviously these are not standard conditions. We're going to get a non-standard value of E. All right, so the first thing we want to do is put these together to get our E0. So we've already decided that Y is the one that's getting reduced. So let's put that one down as a reduction. Y3 plus 3 electrons goes to Y. And we're going to put the E0 down, 1.200 volts. So that's the one that's running as reduction. The other one must be running as oxidation. I always put the arrow first so I can get everything lined up. X2 plus 2 electrons. And then over here we're going to have X. Now this one's being reversed, so there's the minus sign. But notice it's already negative, so be careful with that. That's the minus because we've reversed it. And then this was the actual E0 value itself. So there's your cathode minus anode, if you like looking at it that way. And then, of course, to get everybody to balance, this one would have to be times by 3, and this one would have to be times by 2. But we never multiply these numbers because that's taken care of in the Nernst equation. All right, let's go ahead, make sure our cell reaction comes out the way it should, and make sure our voltage comes out what we need. Okay, so 1.2, and then we're going to basically add 0.75. That gives us 1.95 volts. By the way, if you haven't figured it out already, if you get a number here that's bigger than 6, you definitely did something wrong, because the biggest numbers we have are plus and minus about 3 volts. Now let's check this. So our 6 electrons are going to cancel, because you've got 3 lots here, 6 electrons, 2 lots of 3, 6 electrons. So 2Y3 plus 3X goes to 2Y plus 3 lots of X, 2 plus. All right, solid, aqueous. Why did I do that? 2 things. First of all, to check it makes and agrees with up there, which it does. Second of all, I can write my Q out now. So we've got products over reactants. This one's a solid, so it doesn't feature, its activity is 1. Then we have X2 plus, and it's to the power of 3, because its stoichiometric coefficient is 3. Then on the bottom, this is a solid. Sorry, bad handwriting. This is a solid, so its activity is 1. And then we've got y3 plus. And we square it. Might as well plug the numbers in. If we go up to the top, we can see that y3 plus is 0.33 molar. So, okay, 0.33. And that one's squared. And then our x2 plus was 0.044. 0. And I'm double checking. Yep, 0.440. Not writing molar because remember they'd both be divided by the 1 molar standard concentration. So we don't have any units now. That's why you can put pressures in, because the pressures will be divided by the standard pressure of 1 atmosphere. All right, so now I'm going to do this, 0.044. I want to put it to the power of 3. 0.044 cubed. Then I'm going to divide it by 0.33 squared. And we get 7.82 reoccurring. It's my little way of writing reoccurring, times 10 to the minus 4. All right, last thing now is to do E equals E0 minus 0.0591 over N log Q. I'm going to use this version because it doesn't say anything about it not being 25 degrees C. Since it doesn't say anything about it not being 25 degrees C, I'm going to assume it is 25 degrees C. So we have 1.95 volts here. Oops, that shouldn't be an equal, should it? It should be a minus there. 1.95 volts minus 0.0591 over, can you see? N, 3 lots of 2, 2 lots of 3, so N is 6 log of 7.82 reoccurring times 10 to the minus 4. So that's got it all set up. Now let's just start putting the pieces together. All right, so we've got 7.82 reoccurring. And we're going to take the log of that. So that comes out to 3.1. This part, I'm just going to write some comments above. This comes out to minus 3.10667. All right, so take the log of that. Now we're going to times it by 0.0591 and divide it by 6. And we get this whole part here being equal to minus 0.03. Let's put that a bit bolder. 0.03006. Trying to write down plenty of decimal places just in case. So I just now have to subtract that. But since this is negative and this is negative, that means we add it, of course. So now we're going to put those two together and we get 1.9806 volts. And the answer comes out as 1.981. So there we go. That's a Nernst equation question. As you see, it's important to make sure you do all of the steps because you want to make sure you don't make your Q wrong and you don't want to get your E cell standard wrong. So write out your whole equation, write out your reduction, your oxidation, check your reaction is what you wanted. It's not the reverse. See the other video for details on that. And then make sure that you've got this calculated. Go ahead, get your Q, and then you can put everything together and then go down in here. And there's your answer.